Okay. Uh, in our previous class, we were discussing about the stereochemistry of cycloalkylidene. Cycloalkylidene means a double bond with cyclohexane. Okay. So these type of molecules are called cycloalkylidene. So when these type of molecules exhibit optical activity, it's because of restricted rotation. That means there will be a restricted rotation here. So then when chiral axis is passing through this, so these groups are nearer groups and these two groups are far groups. Always nearer groups takes the priority compared to the far groups. And this passing chiral axis passing, you have to take a decision when you are assigning a R and S configuration to the alkylidene. And so when you are writing this into a format for assigning the R and S configuration, so you can observe that these groups are horizontal groups and these groups are vertical groups. So horizontal groups, when you are viewing from here, OCH3 means methoxy group is on the right hand side. That is the reason this is right hand side. And OH group is on the left hand side. And these two are vertical. COOH is above, H is below. And always the nearer groups take the priority. That is the reason between these two. So this is the one and this one will be the another. And between these two, this will be the 3. So that is the reason uh, a movement from here, this group to here and this group to this group. So that means it is in a clockwise direction. So that is the reason it's called R configuration. So with this, I will go to the next slide. So I will take a pointer so that. Okay. So with this, I will go to the next slide. So next slide, you can observe that. So this is another example of cycloalkylidene moiety. And here, when a chiral axis is passing through this, you can observe that these two groups are nearer groups and these two groups are far groups. So these two groups are nearer groups means these two takes the priority. So that means here what is there? Iodine is there and here bromine is there. So that means when you are viewing from here, right hand side iodine is there. That means this is iodine. So this takes the priority. So I will take a pencil. Okay. So that means the movement, okay, movement should be like this. That means the movement should be, okay, I'll take a, what is called pencil. Okay. So that means movement should be like this. Oh, it's not, okay. So, right. The movement, okay, here in this one, it is moving like this. So that means it is a S configuration. This you can assign configuration. You will get a S configuration. Okay. So this is okay, okay. Okay, so this one will get a S configuration. Okay, how means, so this is 1, and this is 2, and this is 3. That means it will go a rotation like this. So that is the reason this is S configuration. So now I will take a laser pointer. Right. So then if we are looking into the assigning the configuration for this moiety, so when chiral axis is passing through this carbon atom, these two takes the priority, and you can observe that these two are the horizontal groups and these two are the vertical groups. So when you are viewing from here, NH2 is on the right hand side. That is the reason this is right hand side. And when you are viewing from here, Br is on the left hand side, that is Br is on the left hand side, and these two are vertical. OET is here, O phenyl is here. So nearer groups that will take the first priority, that is the reason this is 1, this is 2, because of high molecular weight. And between these two, phenyl groups take the priority, means phenoxy group. So then movement, how the movement should be from 1 to 2, 2 to 3. So that means it's a R configuration. So this is how you can assign the configuration to the cycloalkyline moieties. So then if we are looking into the Spiro compounds, so these type of molecules are called Spiro compounds. So this is an example of Spiro 3,3 heptane. So why it is heptane? It contains 7 carbon atoms. You can observe that this is 1, this is 2, this is 3, this is 4, this is 5, this is 6, this is 7. 7 carbon atom containing Spiro compound. So these two carboxylic acid, 2,4 dicarboxylic acid. So what you can observe, this moiety is one plane, and this will be in another plane. This will be the horizontal, this will be the vertical one. Because of that, this type of Spiro compounds exhibits optical activity, and then when a chiral axis is passing through this, so then what you can observe, these two groups are the horizontal groups, and these two groups are the vertical groups. So vertical groups you can write H and COOH. Horizontal groups means when you are viewing from here, COOH is coming on the right hand side. That is the reason this group is right hand side. So you have to give the preference to the nearer groups. That means these two takes the first priority. That means this is 1, this is 2. And of course, this is 3, this is 4. So when you are moving 1 to 2, 2 to 3. So that means it is in a anti-clockwise direction. Similarly, you can also assign R and S configuration to this Spiro compound. So here what you are observing, these two groups are nearer groups, and these two groups are horizontal one, these two groups are vertical one. So when you are viewing from here, CH3 is coming on the right hand side. That is the reason this is right hand side. H is on the left hand side. Of course, these two are vertical one. NH2 top, NH2 is here, and this is H. And you can consider that this is not NH3, this is a NH2. So then when you are giving the priority, this is 1, this is 2, and this is 3, this one is 4. Then the movement, so it will move from here to here like this. That means this is a R configuration. So with this, I will go to the next slide. So few more example of Spiro compound. Here you should be able to differentiate. You should know what is the difference between the isobutyl group, isobutyl group, N-butyl group, tertiary butyl group, secondary butyl group. And here the priority between the isobutyl and N-butyl. So isobutyl, there will be a more branching. So that means a secondary carbon. This isobutyl contains secondary carbon. N-butyl contains the primary carbon. That is the reason this takes the priority. compared to this one. Between these two, tertiary butyl and secondary butyl. This is a secondary carbon, this will be the tertiary carbon. So tertiary carbon takes the priority compared to this one. Once you know the priority, when the chiral axis is passing through this, these two groups are nearer groups, these two groups are the far groups. So when you are viewing from here, this isobutyl group is coming on the left hand side, that is this, and N-butyl is coming on the right hand side, that is this. Vertical ones. So vertical means tertiary butyl is this, secondary butyl is this. When the priority 1, 2, tertiary butyl 3. So that means it will be moving from here to here, there to here. That means it is a S configuration. Similarly, one can assign R and S configuration to this Spiro compound. This also a Spiro compound. What you need to account here, this is nothing but a A, B. This is A, this is B. Similarly, this is A, this is B. Okay, so what will happen? So when a chiral axis is passing through this, and what you can observe, this is in one plane, this is in another plane, and these two groups are horizontal one and these are vertical one. So these groups are takes the priority. That means vertical means oxygen is here, CH is here. These are horizontal groups means left hand side CH is there, that is this. Right hand side O is there, that is this. So then when you are giving the priority, this is 1, this is 2 and this is 3. So that means the movement is like this. So that means it's a S configuration. So with this, let's go to the next slide. So this is also another chiral compound. So what you can observe, there is a chiral axis passing through this, and you can observe that all the groups are same, isn't it? When the line is passing through this, then you can say that it's have a plane of symmetry. But when a chiral axis passing through this, and one more thing, this moiety. So these two groups are the horizontal one, these two groups are the vertical one. Because of difference in plane, so this moiety is a dissymmetric, and this exhibits the optical activity. So once it is exhibiting optical activity, when the chiral plane is passing through this, so what you can observe, NH, these two groups are the horizontal one, NH is on the left hand side, that is this. CO is on the right hand side, that is this. And these two are the vertical groups. CO is top, NH is bottom. So when you are assigning the priority, nearer groups that take the priority, that means this is 1, this is 2, that means this is 1, this is 2. And vertical groups, CO and NH takes the priority. This is the 1, 2, 3. So when the movement is like this, that means it's a R configuration. So similarly, this moiety also exhibits optical activity. So you can, when the chiral axis is passing through this, so these two groups are the nearer groups, and these two groups are the vertical groups, and these two groups are in horizontal plane. So when you are viewing from here, COH is on the left hand side, that is COH is on the left hand side, H is on the right hand side, and these two are vertical, pH is here, H is here. So when you are assigning 1, 2, 3, so that means it's a anti-clockwise direction. So that means it is a S configuration. So when you are assigning the configuration, in all these cases, what you need to do, you need to take the decision of passing a chiral axis passing way, that you have to take the decision. So then let's look into the stereochemistry of biphenyls. So biphenyl means this is one phenyl group, this is another phenyl group. So these biphenyls also exhibits optical activity. So how means there should be a restricted rotation around the carbon-carbon single bond between the two phenyl group. How there is a restricted rotation? Only when a bulky groups are present at the AB and AB. So in this case, this group is also A, this group is also A, this group is B, this one is B. So what it means, if the same groups are attached between these two positions, then such compounds are achiral. Okay? And suppose if there is A and B and A, in such cases, these type of molecules are chiral because different one. So this, what it means, overall, what we can say that A dash should be different. B dash should be different. That is the chiral, that is the condition you need to remember. And one more thing you need to remember. So these two groups should be bulky enough. If there is a bulky enough, then only there will be a restricted rotation around the carbon-carbon single bond between the two phenyl ring. So, and one more thing you need to observe that, so one phenyl ring will be in one plane, means horizontal plane, other will be in the vertical plane. So in biphenyl, you can found that two planes, one is horizontal, another one is the vertical one. So because of that, this biphenyl exhibits optical activity. Suppose A and A is same, then these kind of moieties are achiral one. B and B dash is same, then also its type of compounds are achiral compounds. What is the criteria? AB and BA is the criteria. So these type of molecules exhibit chiral compounds. And suppose if a compound like this, so here you can observe that A. So this is okay, this is exhibit optical activity, but because of there is a interaction, steric hindrance, this will be little unstable. So but when this NO2 is coming over here, H is going that side, so then that moiety is stable. Okay, this one is stable. So let's look into the few more examples of biphenyl, and also let us assign the R and S configurations. So in this, let's go to the next slide, and overall you need to remember that biphenyl compounds exhibits optical activity because of the restricted rotation around carbon-carbon single bond between the two phenyl ring. And one more criteria, A and A should not be, because both the groups should not be the same. That is the thing you need to remember. So I will go to the next slide. So slide is not moving. Okay, what I will do? Now it's moved. Suppose this is the best example. So what you can say that this is a 6, this is a 6 dash. So 6 comma 6 dash, dinitro, biphenyl, dicarboxylic acid. Here is there 6 comma 6 dash, dinitro, phenylic acid. So this compound is uh, best example for biphenyl optically active compound. So these are the conditions. The restricted rotation condition means features of the biphenyl compounds. The restricted rotation around carbon-carbon single bond of two phenyl groups. Bulky groups must be present to prevent the rotation. Bulky groups must be present at ortho or meta position to prevent the racemization. This is the example. If the groups are bulkier, then the two phenyl rings rotate in such a way that the perpendicular to each other. That is the, so because of that only this biphenyl compounds becomes non-coplanar and they lose this one. So with this, I will go to the next slide. Here, I will explain about how you can assign the R and S configuration to the biphenyl compounds. So when you are looking into the biphenyl compound, you need to observe that, so there should be one side, either of the two benzene ring, there should be a thick line. So thick line indicates that group is horizontal one. So there is no thick line means that phenyl ring is on the vertical plane. So afterwards, if A and A dash is different, B and B dash is different, then a chiral axis you need to draw. So after drawing a chiral axis, what you need to observe from here, when you are observing from here, these two groups are the nearer groups, these two groups are the far groups. Once you know the nearer groups and the far group, then assign the priority. So this is nitrogen and this is carbon. This is the higher number one. This is the reason this takes the first priority. This one is the second priority. And here, this is the third priority. So, and one more thing, you need to assign that these two groups are the nearer groups. That is the reason takes the priority. And when you are viewing from here, these groups are vertical groups. So COOH is on the top, NO2 group is on the bottom. So there is a thick line one. So these groups are the horizontal one. When you are viewing from here, NO2 is coming on the left hand side. That is the reason NO2 is on the left hand side. COOH is on the right hand side. So 1, 2, 3. So the movement is like this. So this movement is called anti-clockwise direction, and this is called S isomer. So it is more stable and resolvable. Resolvable means one can isolate R and S configuration. So when you are taking this kind of moiety, so when you are passing the chiral axis from this side, then these groups takes the nearer groups and these groups are far groups. And here what you need to remember, so these groups are horizontal groups and these groups are vertical groups. So vertical means H is this, H is this. So next to the H, Br is there. That is accountable. So that is the reason I have written here. Of course, just by looking, these two are same. But when you are going to the next carbon atom, a different Br is there, but here H is there. So that is the reason this takes the priority. This is 1, this is 2. And when you are moving here, you can observe that COOH, when you are viewing from here, COOH is on the right hand side. That is the reason COOH is on the right hand side and NO2 is here. So when you are moving like this, 1, 2, 3. So this direction is called anti-clockwise direction, and this is biphenyl showing the S configuration or S isomer. So let's look into the one more example. NO2, COOH, methoxy and H. When the chiral axis is passing through this, in this way, these two groups are nearer groups and these two groups are far groups. So nearer groups means takes the priority 1, 2, and here this will be the 3. So and one more thing, so this moiety is the vertical one and this is the horizontal one. So horizontal means when you are viewing from here, NO2 is on the left hand side and this will be the COOH is on the right hand side. And this is the top and this one will be the bottom. And you need to give the priority to these two groups because of nearer groups. So this will be the 1, this will be the 2. That means this is 1, this is 1, 2, this is 3. Then the movement is like this. That means it's an anti-clockwise direction. That is the reason it is S configuration. And here what you need to remember, the bulky groups adjacent to the ortho substituents. Okay, bulky groups adjust. Of course, this is ortho, this is also ortho, this is also ortho, this is also ortho. So what it means, the bulky group adjacent to the ortho substituent exerts buttering effect. Therefore, racemization is much lower. Okay. So with this, I will go to the next slide. So next type of stereochemistry of Ansa compounds. Ansa compounds means, I will show the example. You can look into that. These type of molecules are called Ansa compounds. What you can observe, so this is a big polymethylene group. And here the N should be, suppose N is equal to 8. So then such compounds are stable. And N is equal to 9. That's also a stable, but n is equal to 10. So that's again, here you can observe that I have mentioned that n is equal to, okay, n is equal to 8 is stable, n is equal to 9 is racemized, n is equal to 10 is a non-resolvable. So that is the thing you need to remember. So these type of molecules are called Ansa compounds. Here what you need to do, you need to select the pilot atom. So how you will select in such a way that if there is a substituent on this side or this side. Suppose substituent is one of the phenyl group is a substituent is having this side, then this side will be the taken as a pilot atom. Suppose a substituent is here, then you have to take this CH2 as a pilot atom. Once you have choose the pilot atom, since you have choose this as a pilot atom, the numbering starts from this oxygen. 1, 2, 3, 4. That's what I have given here. So you can observe that this will be the pilot atom, this will be the second, this will be the third one. So what will happen? So there is a movement like this. So this is called anti-clockwise direction, and it is a S configuration. This is how you can assign R and S configuration to the Ansa compounds. Ansa compounds are nothing but a para positions. Heteroatom will be the present. Heteroatom may be a oxygen, may be a nitrogen, may be a sulfur. So a phenyl group having two para positions are substituted by heteroatom, and those are linked with the polymethylene groups. Okay, when n is equal to 8, such Ansa compounds are stable. N is equal to 9, and those are racemizes. N is equal to 10, those are non-resolvable. Okay, so in such cases, you need to select the pilot atom. Pilot, how you will select? So just look into the substituent present in the benzene ring. So based on that, if the substituent is nearer to the oxygen, that oxygen substituent, oxygen containing CH2 group is taken as a pilot atom. Once you selected the pilot atom, you are numbering that heteroatom first. Next is continuous like this. So this moiety is taken as a S configuration. Let us take one more example of Ansa compounds. So here what you can observe, this is the substituent. So that is the reason this carbon is the pilot carbon. Once you selected the pilot compound, then 1, 2, 3, 4. So that means again how it is going? It is going like this. That means it's a anti-clockwise direction. If it is an anti-clockwise direction, means this moiety exhibits S configuration. So similarly, what you can observe here, I am taking here, you can observe that the benzene is having substituent here. So that is the reason this carbon is taken as a pilot atom. Once you choose the pilot atom, then you can numbering 1, 2, 3, 4. So that means movement like this. So you can observe that this movement is called clockwise direction. So clockwise direction is called R configuration. So with this, I will go to the next slide. So you can observe that this is another example, and of course, so this will have a chiral axis like this, and this will be the N. And you can observe this carbon atom, you can select it as a pilot atom. Once you selected this as a pilot atom, this will be the 1, 2, 3, 4. So it is a clockwise direction. So clockwise direction means it's called R isomer. So similar to the Hansa compound, there is a other compounds called cyclophanes. So this cyclophanes, what you can observe, so there will not be any heteroatom, but two rings are just above the one above the one each other. What here you can observe that, if of course this one will have a plane of symmetry, this kind of one does not exhibit optical activity. But if there is a substituent, at least one ring should have a substituent, and such cyclophanes exhibits optical activity. So let's take example. You can observe that this kind of compounds are called cyclopeans, and this what you call phenyl ring is having a substituent, and then you have to take this as a pilot atom, and here this carbon takes the first priority, this one is the second, this one is the third. So then the movement is like this. That means it's a anti-clockwise direction. That means this moiety is a exhibits S configuration. And here, if you are taking one more example of cyclopeans. Cyclopeans means there is no heteroatom. If there is a heteroatom, then such compounds are called Ansa compounds. If there is no heteroatom, then such compounds are called cyclopeans. And here, what you need to take this as a pilot atom because substituent is present here. So 1, 2, 3, 4. So the movement is in a clockwise direction. So because of that, this moiety is showing R configuration. So what I will do with this, I will go to the next slide. So next is one more example. So here there are two substituents you can find. This is iodine and this one is bromine. So of course iodine takes the priority because the molecular weight of iodine is more compared to the bromine. So that is the reason this group takes the pilot carbon, and this is the 1, this is the 2, this is the 3. So that means movement is like this. So it's a movement is called clockwise direction. So that is the reason this one is exhibiting R isomer. Okay. So I can go to the next slide. So next slide is about the helicity. Okay, I think you are aware that so left hand side movement. So if the left hand side is moving like this, then it is called P, and the right hand side is movement. If it is moving like this, then it is called M. That's what you need to remember. So M, left hand side movement like in a clockwise direction is called P. Right hand side is moving in a anti-clockwise direction is called M. Anyway, I will explain with taking a few more example. And before that, what we need to account, helicity means molecular crowd. So if there is a more molecular crowd such as hexacene, this is called hexacene. Hexacene is the best example, and hexacene exhibits optical activity because of the molecular crowding. Okay, and the stereochemistry here assigned one is P and M. So this one is exhibits P, this one is M. Of course, this is P, and these moieties, one terminal phenyl group should have a substituent. Only such compounds exhibit optical activity. Here phenanthrene, this is the terminal one, and this having substituent, this exhibits P. Okay, and P is nothing but a R configuration, M is nothing but a S configuration. That I will explain. So overall, what you need to remember that helicity means it's because of the benzene ring, more particularly overcrowding, molecular overcrowding. Okay, because of that helicity is exhibited. So we can take the example so that you will be aware. So look here. So P means, suppose if there is a movement like this, A, B, C, D. Okay, if there is a movement like this, you can observe that. What you can observe? Look here. 1, 2, 3, 4. So that means it's a clockwise direction. Clockwise direction means it's a P. And if there is a priority like this, A, B, C, D, that means if there is a movement like anti-clockwise direction, then it's called M. Okay, so let's take example so that you will be familiar. So this here I am taking a halene. Okay, so in this halene, so you know that these two groups are the nearer groups, and these two takes the priority. These two groups are the far group, and this takes next. So 1, 2, so you can observe this is 1, this is 2. So this is 1, this is 2. And then 3. Okay. And then 4. So that means it is moving like this. So what you can observe that. So 1, 2. Okay. And then 3. Okay, anyway, so if you want to assign R and S, how you can, anyway, you are familiar with this converting into a easy form to assign a configuration, no? So you know that these two groups are vertical groups, Cl and H, and these two groups are horizontal groups. So when you are viewing from here, this H is on the left hand side, that is this. OCH3 is on the right hand side. So once you assign place these groups, then priority, these two are priority, means 1, 2. And the next one is CH3. That means it is moving from here to here, and then this. That means it is in a anti-clockwise direction. That means S configuration. S configuration is nothing but a M. Okay, so let us take one more example. So that is this one. This is also a alene. So what you can say that OCH3 and H. So when a chiral axis is passing through this, these two are first priority and these two are second priority. So then the movement. So movement should be coming over here. Okay, next is this, next is away from the observer. So what you can do, you convert this into a this form. So these two are the vertical groups because these two are horizontal one. So these two are vertical means OCH3H. Horizontal means when you are viewing from here, H3 CH3 is coming on the left hand side, that is this H. So then 1, 2, 3. So that means you can observe that the rotation is on a clockwise direction. So because of that, it's R isomer. R isomer is nothing but a P configuration. So this is how you can assign R, M and P. So M means yes, P means R. So that's what you need to remember. And here, what you can observe that this is also a alene, but here the chiral axis is passing through this carbon atom, and it will move like this. When it is passing through this carbon atom, these two will be taken as a nearer groups, and these two are the far group. Of course, these two are vertical one and these two are horizontal one. So vertical one you can write OCH3 and this will be the H. And horizontal one, if you want to write, when you are viewing from here, CHO is coming on the left hand side. That is the reason CHO is on the left hand side. So